Hey, good morning, lads and ladies. Welcome back to Calc 1. I'll be goddamned. As soon as I set my phone down and begin this, it starts ringing. I cannot answer that. All right, welcome back to Calc 1. Oh, today we are going to learn a little bit more about differentiation rules. Over the last couple of days, we have about the power rule, how to differentiate polynomials, and the derivative of exponential functions, specifically e to the x. So let's get back into it. I'll turn on my screen share here. Quick note about the poor quality of answers on these. I mentioned, I think to you guys, that I moderate this subreddit. Some of the bullshit that I see here is just so bad. And you would think that a place like this that has a bunch of people who are supposed to be good at real analysis would have a good answer there too, but they really don't. It is a sad, sad thing. All right. MAC2311, section 002. Today is a lecture. Oh, lecture. And the date is what, the 29th now? Yeah, 29th. We'll get this thing to come into focus. There we go. Oh. So today we're going to learn the product and quotient rules. Oh, why is this thing drifting out of focus again? Focus, you fuck. I'll ask you to please be patient with the document camera. I think it's getting close to the end of its life. It shit the bed pretty hard during my office hour yesterday. This is section 3.2. Recall last time, really over the last few times, we cooked up the following rules. We now know the following differentiation rules. I'll write these out in Leibniz notation. We know that the derivative of a constant is 0. We know that the derivative of a constant multiple is the constant multiple times the derivative of the function it was multiplying, like this. We know that the derivative of a power function is the power times that power function with the power decreased by 1. And we also know that the derivative of a sum of two functions or difference of two functions is the sum or difference of the derivatives. All right, this is what we got so far. These are pretty good. These will get a lot of shit done. In particular, because we can split up over addition, subtraction, and we can pop out constants, and we can differentiate power functions, these things, really all 4 of these, or 5 of these, 4 of these are precisely what you need to differentiate polynomials, right? It tells you how to differentiate the constant term, tells you how to pop the constants out of the non-constant terms, tells you how to differentiate the powers of x that show up in a polynomial, and it tells you that you're free to split up polynomials into their pieces. The other thing that we have is that e to the x is its own derivative. This is nice to have. Finally, we have some understanding why people in all of these past math classes have been so damn interested in this function e to the x. It's because it's a fixed point of the differential operator d dx, which is a really big deal. One of the most important areas of mathematics, I should say, if you're interested in in the modern world and what makes the modern world modern, the answer is differential equations. Differential equations is what makes the modern world modern, because it's the language that we use for dynamics, physics, mechanics, all that shit. So, you know, you don't get a car without differential equations. You sure as shit don't get computers. You don't get any of the machines that made the Industrial Revolution without differential equations. Differential equations are just equations relating derivatives to each other. And so this guy right here is kind of like the y equals x of differential equations, right? Saying the output is the same as the input. This is the identity equation for differential equations. So you can kind of think of this as being like, you know, knowing that e to the x is its own derivative is like learning how to graph y equals x in algebra. It's the very start of saying, differential equation, you know, what is this? How is a function necessarily related to its derivatives? Good shit. Okay, so today we're gonna learn some new rules. We're gonna add to this list, right? Specifically, I'm gonna give you two rules. One of them is gonna tell you how to differentiate a product of functions, and the other one is gonna tell you how to differentiate a ratio or quotient of functions. So yeah, let's do it. All right, today we add two more rules to this list. I don't want to undersell anything that I've written in the notes in the past, but these differentiation rules are probably the most important things we've learned so far in the class, right? Understanding how limits work is really, really big deal, because that's what all of these things are built out of. But when it comes to like going and getting shit done later in the class, you gotta know these, and you gotta know the rules I'm gonna teach you here. So, you know, remember this stuff. Product rule first. I think we talked briefly about this the other day. We said, you know, well, if I want to differentiate a product, what's that going to look like? We said that, you know, the derivative of like a constant times some function isn't the derivative of the constant times the derivative of the function. That wouldn't work. That would just always come out to zero because the derivative of a constant is zero. So we need some rule that is consistent with our other rules. And this is just the statement here. So d dx of f of x times g of x is, I'll write it in Leibniz notation first. I think this one looks a lot better in prime notations. This is d dx of f of x times g of x plus f of x times d dx of g of x. Or in prime notation, if you have f of x times g of x, and you want to prime that whole thing, you want to differentiate that product, this is going to be d dx of f of x, or f primed of x times g of x plus f of x times d dx of g of x, or g primed of x. I think most people remember it this way. The idea is you differentiate one piece at a time, and then you add them up. So an example here, if I wanted to find the derivative d dx of x squared e to the x, I can kind of think of this as f, and e to the x is g, So the derivative of f times g, which is what I'm looking for here, should be equal to the derivative of the first function. So I'll write this in prime notation. That's x squared primed times e to the x left alone. So that's f prime times g plus x squared, that's f left alone, times g primed, e to the x primed. Does everybody see it? This way of writing out these things in the prime notation, kind of, I call it schematically, right? So you don't actually do the differentiation, you just kind of write out what you're going to do, is a really big help. You try to do it all at once, you'll make mistakes. You forget, you get lost. I do it, right? If I try to write it all out at once, 4 times out of 10, I'll make a mistake. But if I write it out like this first, never a mistake. So just be careful. Take it one step at a time. So first you come up with your schematic, following the product rule. And now we actually do the differentiation. So the derivative of 2x, this is the derivative of x squared times e to the x left alone. So the derivative of x squared is 2x, and I leave e to the x alone, plus. Now I have x squared, and I need to differentiate e to the x. Well, what's the derivative of e to the x? That's just e to the x. Everybody comfy? Questions on what we did here? All right, it's worth noting you can factor in e to the x out, and what will be left here is 2x plus x squared. So if you really wanted to, you could factor out not just e to the x, but then you can factor in x, and you'd get 2 plus x. And this sort of business is nice, being able to write your derivative in a nice clean form. And I'll be showing you why that's the case pretty soon, right? Because there's lots of things we can do with derivatives besides find tangent lines. But we'll get to that. Questions on the differentiation or the algebra steps here, anything at all? On the formula that was used or why it looks like this? All right. I would like to make a note just to reinforce it. We said it the other day, but note that the derivative of a product is not the product of the derivatives. This is not f primed times g primed, right? Ah, shit. Yeah, note. Sorry, this pen. My good pens are all dying. No. F times g all primed is not f prime times g prime. We could not have taken this derivative just by differentiating this piece and this piece on their own, right? We couldn't. The derivative here is not 2x times e to the x. It's this, right? So this guy is certainly not true, however tempting it might be. I want to go over 1 or 2 more examples of the product rule here. And then we'll move on to the quotient rule. So let's find capital F primed of x, where capital F of x is, let's see, we'll call it x squared minus 1 times x plus 1. This is another case where I can use the product rule if I want. Right? I have here a product of two functions, right? Two functions being multiplied. I can call this one f, little f, and this one little g. And then think about what my product rule says. Product rule says that the derivative of little f times little g, so my whole derivative here is the product of little f times little g, which should be the derivative of the first times the second. So the derivative of x squared minus 1, so x squared minus 1 primed, times x plus 1, plus the first left alone, x squared minus 1, times the derivative of the second, x plus 1 primed. This will work. What do we get? Well, if you differentiate x squared minus 1, this is 2x minus 0 times x plus 1 plus, you will have x squared minus 1 times the derivative of x plus 1, which is 1 plus 0. And then we can clean it up. This is 2x times x plus 1 plus x squared minus 1 times 1. And then you can distribute the 2x. This is 2x squared plus 2x, and then distribute the 1 plus x squared minus 1. So altogether here we get 3x squared plus 2x minus 1. Question. Did I need the product rule here? Or is there another way I could have done this?
You could have just factored out the
out. Remember what we've been saying, if you can ever just like do some algebra to clean things up before you get started, you should. And this is a great example of one of those. So compare the amount of work that took compared to doing some algebra with capital F at the start. If I FOIL that out, I'll even write it here, x squared minus 1 times x plus 1. If I FOIL this out, I'll have x cubed plus x squared minus x minus 1. And now this regular polynomial in standard form, so I can differentiate this just using the rules that we already know, right? The rules that we knew before the product rule, namely the power rule. X cubed becomes 3x squared plus x squared becomes 2x minus x becomes 1 and minus 1 becomes 0. So f primed is just 3x squared plus 2x minus 1. I know which of these I would rather do. One of them is much faster. I was even silly here, and like I rewrote the original function, taking up extra space. And in actual fact, all I had to do is like this and this. It's like nothing. Compared to the product rule up here where there's room to make mistakes, right? More room to make mistakes up here doing all of this than there is down here doing this. So wherever possible, avoid using more complicated rules than necessary.
I have a question.
Yeah.
So with all this, it's on our test, and when we like show our work, it's okay to do the easier version. Mm-hmm. You're just like checking for accuracy.
If a problem yields to a simpler method, I would prefer that you use the simpler method. Yeah, I mean, if on an exam I asked you for the derivative of this function and you did this instead of the product rule, I would be quite proud of that. I would consider that a better answer than the above use of the product rule, because it shows critical thinking. It shows that you recognize that there are multiple ways to solve the problem and that one of them was faster and cleaner. So certainly, yeah, on a test, if there is a nicer way to do the problem, do it the nicer way, by all means.
Okay, thank you.
But yeah, wherever possible, avoid using more complicated rules than necessary. And specifically, try to simplify algebraically before applying product, or I'm going to say here, or quotient rule, even though we haven't quite talked about the quotient rule yet. So this is it's a valuable note. It really is, especially when it comes to the quotient rule. And I'll show you some examples with that in just a second. Anything else I want to show you with the product rule? Yeah, there's one other sort of problem I want to show you with the product rule before I introduce the quotient rule. Last call for questions on either of these two examples we've done here. Even though this isn't the best way to solve the problem, it is important that you're able to follow what we did with the product rule here. So if there are any questions on what we did with the product rule there, please don't hesitate to ask. Okay. So one more with this. Suppose f primed of 0 is 2, f of 0 is -1, let's just leave it at that actually, and find the slope of the tangent line to the function. Let's do g of x equals f of x times e to the x at x equals 0. This one a little more abstract in its setup, but still at its heart a product rule thing. You do have a problem or two like this in your homework, and that's why I wanted to show you these, where that things are not given to you explicitly, but you have to kind of, again, set them up schematically and infer from the information given. What am I looking for here? What am I being asked to find?
The slope.
Good, yeah, the slope of the tangent line. To what function?
G of x?
Yeah, g of x, right? So what do I need to find the slope of the tangent line to the function g of x?
F of x?
Think more simple, right? So if I'm saying find the slope of the tangent line to whatever function, what are we looking for? We're looking for.
Don't you need a point and like the y-intercept, or?
If I wanted the equation of the tangent line, sure. But here I'm just asking for the slope of the tangent line. So where does the slope of the tangent line to the function g of x come from?
F of 0 equals -1.
The derivative?
Yeah, the derivative, right? If I want the slope of the tangent to the function g of x, I need the derivative of g of x, right? Specifically, I'm looking for g primed of 0, because this is the slope of the tangent to g of x at x equals 0. I know you guys all know this. It's just a matter of like turning off enough of the chatter in our brain to realize which piece we're really after. So g primed of 0, that's the slope of the tangent to g of x at x equals 0, right? That's what we need. We're looking for the slope of the tangent line for this function, which means I need the derivative of this function at 0. How could I possibly get g primed of 0? Well, it would be dope if I had g primed of x, right? If I had the derivative g prime, then I could just plug in 0. But g of x wasn't given to me explicitly. It was given to me in this weird way where they said, okay, g of x is some function f of x times e to the x. So first, are we all comfy with why we're after this thing? Okay. So let's calculate g primed of x to the best of our ability. Well, g primed of x is the derivative of g of x, right? So that's the derivative of f of x times e to the x, because g of x is f of x times e to the x. And this is a product. So if I want to differentiate this product, I use the product rule. I differentiate the first function and I leave the second function alone. And then I add that to what I get when I leave the first function alone and I differentiate the second function. Does everybody recognize how this is the product rule output from this? It's like f times g. I'm differentiating f times g. It's just the labels are weird. So if I want to differentiate this product of two functions, first I differentiate the first function, leave the second function alone, and then I add that to what I get when I leave the first function alone and differentiate the second function. Now the derivative of f primed, I have no idea what that is. It's just f primed of x. Nobody told me what f of x was, so I can't compute that explicitly. I just leave it as it is. And over here, similarly, I don't know what f of x is, but I do know what the derivative of e to the x is. That's just e to the x. So here's g primed, which means that g primed of 0, which again is the thing that I want, is f primed of 0 times e to the 0 plus f of 0 times e to the 0. Just plugging 0 in for x everywhere here. Now for the fun part. What's e to the 0?
1.
Good. Anything to the 0 power, at least any finite non-zero thing to the 0 power is 1. So e to the 0 is definitely 1.
Won't we now, for the f prime of 0 and f of 0, go back to the top where we've been given f of 0 and f prime of 0?
Exactly. So this is why you see me zooming out here. We're zooming out so that we can see what is f primed of 0 and what is f of 0. So f primed of 0, I was told is 2. And f of 0, I was told is -1. So this whole apparatus here, g primed of 0 is 2 times 1 plus, I'll write it like this, we can see it, 2 times 1 plus -1 times 1, which is 2 minus 1, which is 1. So the slope of the tangent line to g of x at x equals 0 is 1. That's all. These are good problems. These are problems that are really good at checking whether you understand what the product rule is saying or whatever rule is saying. Problems like these have a way of showing up on exam 1. Hint, nudge, wink. Questions?
When we previously were finding the slope and equation of the tangent line, could we do it this way, like finding the derivative first instead of doing f of a plus h minus f of a?
So we didn't know these differentiation rules back then, right? But yes, every time you needed a derivative in the past, you had to use the limit definition of the derivative, right? So this is something we talked a little bit about on Monday. These things I'm showing you now, these differentiation rules, are shortcuts to get you around that limit definition. That's the whole idea. So it's true that you can go back and solve a lot of those problems from 2.6 and 2.7 using these differentiation rules without ever having to take one of those big massive limits. Now there will be problems. I tried to warn you guys about this back when we were doing those last week. There will be problems on the test that say use the limit definition of the derivative to find blah, blah, blah. And on those problems, you need to set up lim h to 0, f of a plus h minus f of a all over h. You need to show me that you know how to do those things and also how to interpret those symbols. Tell me what they mean and why they're significant. But it's 100% true that once you learn these rules, from here on out, we really don't mess with that limit definition much anymore. And all of those problems can be made much, much faster through these differentiation rules.
Okay, thank you.
Of course.
I had a quick question about the calculate g prime of x. How did you know to do g prime of x when it's asking for g prime of 0?
Because they told me to find the slope of the tangent line specifically at x equals 0. All right, so they said find the slope of the tangent line here at this point.
Okay.
So I identified first that what I needed was g primed of 0. And then the best way to get g primed of 0 is to calculate g primed of x and then plug in 0 for x.
Okay.
Does that make sense?
Yeah.
All right, I am going to go ahead now and move to the quotient rule. Sorry, any other questions on this? Okay, yeah, let's start talking about the quotient rule. Some fractions we know how to differentiate by splitting up and using algebra. We saw some examples of those the other day as answers to Robert's question. But others, not so much. So the quotient rule tells us how to differentiate a quotient or a ratio of two functions, a fraction. This says that the derivative, I'll need some space for this, that the derivative of f of x over g of x, so if you have a quotient of two functions like this and you want to differentiate the whole thing, then this is d dx of g of x times f of x. Oh wait, shit. Hang on one second. This is one of those things where when you're teaching it, you get nervous and you forget the order. I want to make sure that I don't write this wrong for you guys. The order of the top, I always get nervous here. So where is it? Product quotient rule. Yeah, this is not this. It's all good. Yeah, I was about to start writing this down backwards. All right, here. So this, the derivative of f of x over g of x is the bottom g of x times the derivative of the top minus the top f of x times the derivative of the bottom all over the square of the bottom. And in the Leibniz notation, it looks pretty intimidating. It looks pretty bad. It looks nicer in prime notation, but still pretty bad. Says that f of x over g of x all primed is the bottom g times f primed minus the top f times g primed all divided by g squared. The way people remember this is as low times the derivative of the top, d high, minus high times d low over low times low, or low. So you'll hear people kind of reciting this under their breath during calculus tests a lot. Low d high minus high d low over low. It's a mnemonic for remembering the quotient rule. And the mistake that's easy to make here is switching up the order of the numerator. So low d high minus high d low. You got to remember it in that order. Very easy to make that mistake. You saw me start to make it up here. If you do that, it will just change the sign of the derivative because you're swapping the order of the subtraction. So it will change things if you get the order wrong. It's important that that doesn't happen. But yeah, this is how you differentiate a quotient. It's not very pretty. It's kind of fucking gnarly. I'm not going to bother going through a proof for this. I can prove it for you cleanly once we have the chain rule. The proof for this right now, like the proof of the product rule, is just a lot of symbol juggling. If you want to see them, I do have links to the proofs in the module. If you go down to the 3.1, 3.2 stuff in the modules for differentiation rules, there's proofs for all the differentiation rules linked there. But it's not a pretty proof. It's just a bunch of like juggling around symbols. So I won't go through it here. It doesn't give you any insight. That's a good question, Mackenzie. So we're saying, Mackenzie's asking, since the order matters here, does the order matter in the product rule? The answer there is no. The order in the product rule really doesn't matter because both of the terms are positive. So it's like f times g prime plus g times f prime. You can swap those around and it won't change anything. F times g prime plus g times f prime, or g times f prime plus f times g prime. They will always come out the same either way because they're being added, not subtracted. In the same way that 2 plus 1 is the same as 1 plus 2, the order of the product rule doesn't matter. But 2 minus 1 is not the same as 1 minus 2. When you're subtracting, the order does matter. So here, because we're subtracting in the numerator, the order of the quotient rule really does matter. But in the product rule, the order that you do the two groups, because they're being added, really doesn't matter. So good question. You can see how complicated this is just schematically. And so take that note from earlier to heart. If you can avoid using one of these rules, by all means, avoid doing it, right? If you can get around having to use the quotient rule by simplifying this thing using algebra first, if you can simplify it into a polynomial or string of power functions, do that. Don't do this if you don't need to. But there are plenty of times when we do need to do this. So let's see some of those examples. I'll do a small one down here. So let's find the derivative d dx of x over e to the x. It's not much I can do here to simplify, right? There's no way e to the x and x don't have any common factors. There's no nice way to combine those guys. So I'm going to think of this up here as f of x, and this down here as g of x. So following my quotient rule, the derivative of f over g should be, I'll write it out schematically again, low d high. So the bottom, e to the x, times the derivative of the top. And I'm just going to write it out schematically in this prime notation without actually taking the derivatives. Minus high, the top, times d low, the derivative of the bottom, all over low, the bottom squared. And these parentheses, when you square something like e to the x, are important. So quick sidebar here. E to the x squared, this is kind of ambiguous. This always means, when you see it like that, e to the x squared like this, which is different from e to the x all squared like that, which is actually e to the x times e to the x, which is e to the 2x. Just a little comment on notation. So the parentheses downstairs are important. Right, when I square to e to the x like that, we need to write it in parentheses. Okay, so now I've schematically written out my derivative. Let's go ahead and do the calculation. The derivative of x here is 1. So this is e to the x times 1 minus x here just stays x times the derivative of e to the x, which is e to the x. And all of this is being divided by e to the x all squared. I can just leave it like that for now, or I could write it as e to the 2x if I wanted. And this can be simplified, and it should be. I can factor in e to the x, right? I'll write this as e to the x times 1 is just e to the x minus x times e to the x. And this is all over e to the x all squared like this. And you notice in the top here, I can factor out an e to the x. So let's do that. If I factor e to the x in the top, what's left here would be a 1, and what's left here would be an x. This is 1 minus x. And it's still being divided by e to the x all squared. And now e to the x over e to the x all squared, those can cancel. And I get 1 minus x over e to the x. So here's this derivative nicely simplified. Questions on this first line? Is everybody comfy with where these are coming from? There's low times d high, or g times f primed, minus f times g primed all over g of x squared. And in this line, I just calculated each of the little primes. So the derivative of x primed, is 1. The derivative of e to the x all primed is e to the x. And then here I didn't do much. I just said, oh, okay, well, e to the x times 1 is e to the x, and x times e to the x is x times e to the x. This helped me see that I can factor out an e to the x from the top. And once I factored out that e to the x from the top, I recognize that there's also a factor of e to the x in the bottom. This bottom is e to the x times e to the x. So when I cancel one of those, there's 1 e to the x left over downstairs. Everybody comfy cozy? Any questions on this? Okay, let's look at some more examples here with the quotient rule. Let's find capital F primed of x, where capital F of x is, and this is one of my favorite functions, 1 over x squared plus 1. The graph of this function is really neat. If you haven't seen it before, I'll show you in Desmos really quick. You don't need to draw this. But it is a neat looking function here. It's kind of like what we call a bump function for the obvious reasons, right? It's mostly flat, but then it's got this bump. Turns out to be intimately related to the inverse tangent function. And I'll, just for fun here, get these juices flowing in your brain. You may notice an interesting connection between the blue and the red here. I'll let you think about what that connection might be. We'll prove it next week.
Isn't that the graph of the derivative of the tangent?
So the blue here is the inverse tangent, arctan, and the red here is indeed the derivative of the blue. All right, notice over here, the red is small but positive, so blue is increasing, but it's increasing slowly. As the red gets bigger, the blue increases faster and faster. At 0 here, the blue's tangent line would have slope 1. The y value on the red graph here is 1. And then the blue function continues to increase but dies off. That corresponds to the red continuing to be positive but getting closer and closer to 0. So yeah, red is the derivative of blue. We'll prove that next week. But for now, I want to go in the other direction. I want to differentiate this, right? I want to take the derivative of this thing. So I know that what I need, capital F primed of x, is the derivative d dx of 1 over x squared plus 1. So I can think of my little f upstairs here as being the function 1, and my little g downstairs as being x squared plus 1. So when I go to take this derivative, I'll have the bottom times the derivative of the top. And I'm just going to write it out schematically, times 1 primed minus the top times the derivative of the bottom, which is x squared plus 1 primed. all divided by the bottom squared. And remember, when you square x squared plus 1, that's not x to the 4 plus 1. You need to square the whole thing, right? So now I have to compute the little primes upstairs. I have to figure out what each of these little derivative pieces are. X squared plus 1 is just x squared plus 1, but 1 primed, the derivative of 1, that's 0. And then we'll have minus 1 times the derivative of x squared plus 1 is 2x. 2x plus 0. The 1 differentiates to 0. And downstairs, we just have, I'll leave it as x squared plus 1 squared. A note on algebra. I know in your pre-calculus classes and algebra classes of yore, oftentimes people want to FOIL these things out, right? That we have this innate desire anytime we see a binomial raised to a power to just go ahead and start multiplying it out. Don't do that. Leave it factored. If anything, factor it further. Try to factor more, but don't unfactor unless you have a real good reason to do so. All right, let's see what we get. This whole piece is going to be 0, right? I've got x squared plus 1, but it's all being multiplied by 0. So this piece is gone. And over here, I'll just have negative 1 times 2x. So this is going to be negative 2x over x squared plus 1 squared. And that's it. That's the game. I want you to imagine for a minute, let's come back to this Desmos graph and get rid of the arctan thing. I don't care about him right now. Imagine for a minute that I asked you to find where this function has a maximum. We'll talk about this stuff in detail soon, but just think along with me for a minute. Looking at this picture, not too hard to see, right? We got a local max right here. We are increasing, whoop, decreasing. That means I rolled over the top of a hill. What's the slope of the tangent line up here at this max?
0.
Yeah, it's a horizontal tangent line. So if you wanted to find this maximum, if you didn't have the graph, but you wanted to hunt it down, you would look for a place where the derivative is 0, because at maxima like these, the tangent line is horizontal. So if I was hunting for the max, I would take f primed, this thing, and figure out where it's 0. And evidently, if you plug in x equals 0, right, you get 0 over 1. So you see the connection there. This place where I have a max value, a local max along this graph, happens to also be an absolute max here, comes from the derivative being 0. And that's a nice connection. That's a connection that we're going to use a lot immediately after exam 1. All right, how am I doing on time? We got a few minutes left. Questions on this calculation?
What if it was for a minimum?
Good question. So let's look at a different example real quick. So here's a max and here's a min, right? Both of these, though, give me horizontal tangents. So whether you're looking at a max or a min, any place where you've got a neat thing like that going on, a min or a max, is going to be a place where the tangent line is horizontal. If the function is smooth. Now there's exceptions to these. If the function is not continuous or is not smooth, then those rules don't work. But if you know your function is everywhere nice and smooth, no breaks, no jumps, no hard corners, then you can always find maxes and mins by looking for horizontal tangent lines, looking for places where the tangent is horizontal. Pretty cool stuff, right? So we will definitely come back to this and we'll spend a lot of brain power on this, but after exam 1. Before exam 1, we're going to worry just about the basics. Any other questions on the calculation here? All right, I'd like to do one more. Let's find, I'll use different notation here. Find dy dx where y equals 2x minus 1 over the square root of x. Nothing special would happen for this. If you FOIL that out, you get x to the 4 plus 2x squared plus 1. And that would be what you'd have downstairs, but there's nothing special about it. It won't help us cancel anything because we can only cancel common factors. So if you want to cancel, you got to factor. You can't, FOILing out doesn't ever help you cancel. There's nothing for that denominator to interact with. So there really isn't any benefit to multiplying it out. But there can be benefits to leaving it factored. Namely, can help you see what cancels and what doesn't. So if we want to see it, here, let me come back to this for just a second. If we want to see what this looks like, it would be negative 2x over x to the 4 plus 2x squared plus 1. That's what that would look like. But it doesn't teach us anything. It doesn't show us anything. It's not like I can cancel any of these x's with this x because you can't factor an x out from the bottom. I can't cancel this 2 with that 2 because I can't factor a 2 out from the bottom. So the only kind of reason you would ever want to do algebra after differentiating is to hopefully clean up, cancel, simplify in some way. But FOILing this out doesn't help us simplify anything. In fact, it does the opposite. If we wanted to cancel or clean up or simplify, we would try to factor the top and factor the bottom and look for common factors that could be canceled. So certainly we can do this. It's not wrong to do this. It's just not helpful. Yeah, no problem. All right. I want to find dy dx. Here's why. What do I do? Y is this big old quotient. So which rule should I use?
Can't you change the square root of x into x raised to the negative 1/2?
So I have the following algebra options regarding the square root of x. I can leave it downstairs as x to the 1/2 like that, or I could move it upstairs. This would be 2x minus 1 times x to the negative 1/2 like this. Those are all kosher moves. We need to make sure we have these parentheses here if we're going to move this upstairs, because everything, remember, these fractions are grouping symbols, so really we always think of them like this. I just don't usually write those parentheses. And this is true, but I'm not sure it's super useful. There is a neat thing here with this last form. If I know how to differentiate this and I know how to differentiate this on its own, then I could use the product rule here, right? Instead of using the quotient rule here or here. So let's see how this comes out if we do a few things. We can use the quotient rule. This says that the derivative that I want, dy dx, which is d dx of this thing, 2x minus 1 over the square root of x, could be calculated as the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. This is for sure one way to attack this problem. Now, when it comes to calculating the derivative of the square root of x, we need to be a little bit careful. So I'll continue this down here. That first piece is root x times 2x minus 1. The derivative of 2x minus 1 is just 2. And then minus 2x minus 1 times the derivative of root x. So we should come off to the side here somewhere and make sure we know how to differentiate root x. Root x primed is x to the 1/2 primed. That's a power rule thing. This is going to be 1/2 times x to the 1/2 minus 1. Well, 1/2 minus 1 is negative 1/2. So this is 1/2 times x to the negative 1/2. And the root x all primed is the piece that goes right here. So this is going to be times 1/2 x to the negative 1/2. And then all that is being divided by the square root of x all squared. Thankfully, the square root of x all squared is just x. Maybe I'll leave it as that for now, just so we're not doing too much in one step. So in this line, all I did is calculate the little primes, right? The 2x minus 1 primed is 2. And the root x primed is 1/2 x to the negative 1/2. I think we'd all agree that this is a little messy looking. Can it be cleaned up? Yes. This first piece is 2 square roots of x minus the second piece. I've got 2x minus 1 times 1/2 x to the negative 1/2. That's 1 over 2 square root x. All right, what's the algebra there? Well, x to the negative 1/2 is 1 over x to the 1/2. So this is 1/2 times 1 over square root of x, which is 1 over 2 root x. And then downstairs, I still have root x all squared, which I'll just go ahead and write as x. This is a little nasty, right? This is not super clean. I can't combine these terms because order of operations wins out. These two are being multiplied. So I'd have to combine these guys before I could do the subtraction. This is going to give me a big fraction, and then I would have to have a common denominator with this piece, and it's going to get a little nasty. It's not wrong, but it's hard to work with. Can we simplify it further? Yes, we can. We can go ahead and have the common denominator here. So I'll write out the first few steps of this. This would be minus 2x minus 1 over 2 root x, like that. And it's all being divided by x. And now if I wanted to combine the two things upstairs, I would have to have a common denominator between this and this. So my next step, we need a common denominator upstairs. So I would multiply 2 root x top and bottom by 2 root x, because that's what's missing from his denominator. And then all of this is being divided by x still. And now, here, 2 root x times 2 root x is 4x over 2 root x minus 2x minus 1 over 2 root x, all all still being divided by x. Of course, it's like this. And now that I have a common denominator between the two pieces upstairs, I can go ahead and subtract them again, just remembering that all the little fractions have all the little numerators and denominators in parentheses. So when we subtract, that negative gets distributed. And this will be 4x minus 2x plus 1 over 2 root x, and then all divided still by x. And you can see why this is a little bit nasty, right? I'll continue this. And continue this over here. 4x minus 2x is 2x. That'll be 2x plus 1 over 2 square roots of x, all being divided by x. And now finally, I can say, okay, this is 2x plus 1 over 2 root x. Dividing this by x is the same as multiplying it by 1 over x. So this is 2x plus 1 over 2x root x. And that is my derivative, simplified as nicely as I could hope for. I can't cancel the 2's because the 2 is not a factor of the top. I can't cancel the x's. The x is not a factor of the top. I would have to be able to factor those out in order to cancel them. But since I cannot factor out the 2 from the top, I can't cancel it. I cannot factor the x from the top because this guy doesn't have an x, so I can't cancel it. The most you could possibly hope to do with this from here, the only thing you could possibly hope to do with this from here, is to rewrite the bottom as 2 times x to the 3/2 power. Because x to the 1 times x to the 1/2 is x to the 3/2. Let me ask you a question. Was this fun? Is this in any way enjoyable?
Not at all.
No. And we spent the vast majority of the time, everything from here down, doing algebra. The last calculus step was right here. So, fuck this noise. Right? We don't want to do this stuff. We really don't want to do this stuff. Can we avoid doing this stuff? No. Let's come back here. There is another way I can rewrite this algebraically. We could use the product rule. Product rule also going to be kind of nasty. But 2x minus 1 over the square root of x, that's the same as 2x over the square root of x minus 1 over the square root of x. X to the 1, so this is 2x to the 1 over x to the 1/2 minus 1 over x to the 1/2. Now you just clean these up. This is 2 times x to the 1 minus 1/2 is x to the 1/2 minus x to the negative 1/2. So dy dx, the derivative is 2 times 1/2 x to the 1/2 minus 1 minus negative 1/2 x to the negative 1/2 minus 1, which is x to the negative 1/2. 2 and 1/2 there cancel. 1/2 minus 1 is negative 1/2. Plus minus here makes plus 1/2 times x to the negative 3/2. Done. much better. We're talking 2 lines, 1 line for the derivative. And if you want to simplify this further, if you want to clean this up as much as possible, like we did on that last one, the trick from here is to factor out the largest negative power. So here the largest negative power is x to the negative 3/2. And if I factor that out, I can look and see what's left. This would be x to the negative 1/2 divided by x to the negative 3/2. I'll even write it like that. And this other piece would just become 1/2. X to the negative 1/2 divided by x to the negative 3/2 is x to the negative 1/2 minus negative 3/2, which is x to the positive what? Positive 1? Negative 1/2 plus 3/2. Yeah, it's x to the 1. I'll write it here so you can see exactly what I'm doing. Now, negative 1/2 plus 3/2 is positive 2/2. That's x to the 1. So even if you want to fully simplify things, this is much easier, I think. You get x plus 1/2 over x to the 3/2. Much, much easier to work with.
Could we have left it like where you didn't start simplifying it like that?
Yeah, this is okay.
Okay.
If you want to leave it up there, that's all right. It's true that down the road, we will be doing things with the derivative that will require you to get to a step like this. Like, for example, the thing we talked about a minute ago, finding mins and maxes, setting the derivative equal to 0. Setting this equal to 0, you're not going to be able to see what the solutions are. Here, I can see right away, negative 1/2 is the solution. So that this sort of algebra will be necessary at some point. And this is a replacement for like having a common denominator and going through all the fraction work we did before. I like this. I think this is much, much faster. Certainly the differentiation is easier, but I would contend that this algebra is also easier.
Okay.
You might say,
And
well, this doesn't look like what we had over there. If you multiply top and bottom by 2, then you will get what we had exactly over there. That was 2x plus 1 over 2x to the 3/2.
why did you divide x to the negative 1/2 divided by x to the negative 3 over 2?
So what I'm doing is
Um,
factoring out, right? Factoring is like dividing. When I factor something out, it's like I divide each term by that thing. So imagine you were to redistribute this term. If I was going to distribute this term across these brackets, here, the x to the negative 3/2 would cancel, and you would just get the x to the negative 1/2. And here, you would get 1/2 x to the negative 3/2. So this is just a way to make it easier to see what's going on when we factor out that x to the negative 3/2 term. You could jump from this step down to this step if you're good enough with the algebra. But I inserted these 2 middle steps to help you guys see where this answer is coming from. If you don't like this trick, you don't have to use it, right? You could also rewrite these as fractions, 1 over x to the 1/2 plus 1 over 2x to the 3/2, and then go through the normal common denominator process. But this is a trick that's usually learned in pre-calculus classes that I just wanted to remind you of. I do think that's about all we have time for today, so I'm going to go ahead and end it here. We now know the product and quotient rules, and we've got a good feel for when we should use each. Remember, always, always, always try to do some algebra. If you can clean up your big nasty quotient into a not big nasty quotient, then you don't need to use the big nasty quotient rule, which is nice. Same is true for products. If you can distribute out a product and avoid using the product rule, I encourage you to do that. That's it. These lessons are not terribly brutal. You just kind of need to learn the formulas and get comfortable working with them. So there's plenty of homework problems for you guys to grind on. If you do get stuck on any of those, you can come see me in office hours. You can send me an email. Next week, we are going to talk about the chain rule, and then we will be getting ready for exam 1. So exam 1 is going to come not next week, but probably the week after, and probably early in the week. So I think next Monday, I will lecture on the chain rule and release your first study guide. And then probably the Monday or Wednesday after that, kind of depending on how long it takes us to get through the chain rule stuff, is when we'll have our test. So that's kind of where we're going. I'll talk more about the tests and the study guides and exactly what you need to do. But just know that for the test, you're going to need the webcam on your computer, and you're also going to need Zoom on your phone. I'll be requiring both of those. And then for the study guides, there will be an assignment in WebAssign that you have to complete. But to get credit for the study guide, you need to write out your solutions and submit the scans of those solutions on Canvas. But we'll talk more about that next week. So please just continue working on this homework. If you have any questions, come see me in office hours or send me an email. Otherwise, I will see you guys on Monday.